Welcome to Math with Michelle, where math finally makes sense. Whether you're tackling high school math or diving into college algebra, I'm here to break it down step by step with real examples and zero stress. From algebra to functions, graphs to equations, I've got it covered. Hit that like button and let's master math together. Welcome to Transformations of Functions. I know I've done a video on this before, but with that one I focused more on a square root function and quadratics. This one we're going to be looking at some other types of functions, specifically cubic and quartic. But the other thing I want to talk about, and one thing that we don't talk about enough, is symmetry. So there's two types of symmetry that we're going to focus on here, and those are going to be even and odd. So even symmetry is going to be symmetric to the y-axis. And you're going to look at some of these and you're going to say, well, they're symmetric. There's a line of symmetry. But this is very specific to being symmetric to the y-axis only. Meaning if you were to fold the graph at the y-axis, it matches perfectly. If you have to fold it at the line x equals 2, well, that's not the y-axis, so it's not even. It still has symmetry, it's just not even symmetry. So what that's going to look like whenever you draw a graph, and I'm going to do kind of a messed up one. So let's say we have that on the left, then we're going to have to match that on the right. Let's see, I went 1, 2, 3, 4, 1, 2, 3. So 1, 2, 3, 4, 1, 2, 3. That looks a little rough, but you get the point. It's very much so folding on the y-axis. So even symmetry, fold on the y-axis. So when you look at your table of values, if you pick any number and its opposite, for example, 2 and -2, they both have the same y value. So here the y values must match. And so you could test it that way. Substitute an a value, substitute a negative a value. If you're getting the same answer for both numbers, then it's an even function. Technically, you should substitute a variable. That way you can see that it's actually even for all and not just some of them. But I find it easier to look at it graphically or just test one or two if you're not comfortable using variables to test. So an odd function. This is called symmetric to the origin. Whereas this one was line symmetry, this one's going to be rotational symmetry. Okay. So whereas this came up from 1, 2, 3, 4, 5, 1, 2, 3, -5, -3. This is at -3, 2, -2, 2, and then it has to go through 0, 0. So what we have to think about is if this section were to rotate 180 degrees. So I'm going to go right 2, down 2, right 3, down 2, and right 5, up 3. So if you look here, we could take that brown section, rotate it 180 degrees, and it matches up to the green section. That's what rotational or odd symmetry is. And basically, if you take an a value and its opposite, then the y values must be opposites. So here, if we look at -5 and +5, well, -5 was at -3 and +5 was at +3. Or if we look at -3, 2. So now if I go right 3, I'm down 2. So here, when the x changed signs, the y also changed signs. Here, when the x changed signs, the y matched. Okay. So if f of x equals x squared plus 2x, is it even, odd, or neither? Well, the easy way to do this is just to check 1 and -1. So 1 squared plus 2 times 1 is 3. -1 squared plus 2 times -1 is -1. Okay, the numbers don't match at all. So this is going to be a neither. What about f of x equals x cubed plus 2x? Again, I'll test 1 and -1. So 1 plus 2 is 3. -1 plus -2 is -3. Hey, it looks like they're going to be, since these are opposites, it looks like it's going to be odd. And the reason for that is, if I substitute -x in instead of the positive x that's here, -x times -x times -x is -1x cubed, plus 2 times -x is -2x. If I factor out that -1, so see how this is -1 times the original f of x? That's the other reason why this is odd. So you can do it for a generic variable, but I find it easier to test a number. So again, that vocab word is even or odd. Even meaning symmetric to the y-axis, odd meaning symmetric to the origin. So symmetry is something we talk about a lot about in different algebra classes, and eventually we use it in calculus to help us find some areas under the curve with some of our advanced math. So I did say that we were going to be talking about shifts of graph. So I want to think about the parent functions, y equals x cubed and y equals x to the 4th. And while we would expect these to have more terms than a quadratic, because they are very simple, in fact they're written as a monomial, it'll be a little bit tougher to see those curves. So let's just go ahead and make a table of values for each of them. And I'm just going to go from -3 to 3. -3 to the 3rd power is -27. -2 to the 3rd power is -8. We'd have -1 here. And 0 to any power is 0. 1 to any power is itself. 2 to the 3rd is 8. And 3 is 27. See how they're all opposites? This one happens to be odd symmetry, currently. I say that currently because of something I'm going to talk about in a little bit. -3 to the 4th is +81. And again, that's because when you type it in a calculator, make sure you put the power of 4 on the outside. -2 to the 4th, -1 to the 4th, 0, 1, 16, and 81. These currently, this one is currently even because it's symmetric to the y-axis. The y values match when the x values are opposites. Now, I'm not going to obviously graph these all the way up to 81. We could. But I am at least going to go up to 8. But I am going to adjust my numbering here. I'm going to number by 2's going up and 1's going over. So we have, we won't use blue. I use blue on the other one. We have 0, 0, 1, 1. Notice how I'm very careful with how I did that. 2 was at 2, 4, 6, 8. Negative 1, negative 1. Negative 2, 2, 4, 6, 8. So we're getting our 2 turns. It's just more like an S curve instead of like a switchback. So we got the number of turns, we just only have one x-intercept. I'm going to number this by 1's again. But I'm going to number this by 4. Just to make it a little bit easier to get the picture. So 0, 0. 1 was at 1. 2 was at 16. Negative 1 was at 1. Negative 2 was at 16. So it kind of looks like a parabola, but you'll notice that it kind of bottoms out a little bit extra around 0, and that's just because of the extra power. If you've watched other videos of mine, you know that it's going to bounce at the intercept because it's an even power versus crossing over or cutting through because it's an odd power. So assuming that you can write this as just this format, you're going to get this shape. However, we learned about in other videos HK shifts. And those HK shifts are still going to apply for these. So if I have f of x equals x minus 2 cubed plus 1. That's going to take this graph here and move it right 2 up 1. You might have remembered if you watched other videos that I wrote this x minus h and I used the arrows on it, and I had plus k and I had the arrows on it to remind us that the h was our left right, the k was our up down. That thing carries over a lot. So this graph is going to be 2 spaces to the right and 1 space up. 2 spaces to the right, 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 1 space up. So now that it's been shifted to the right, it's no longer passing through the origin. Therefore, it is no longer odd. This graph happens to be neither. It has symmetry, it just has symmetry to something else, so it is not the special even odd symmetry. Okay? If I said f of x equals x to the 4th plus 5, and we'll put a negative here. Okay, so now the negative says to reflect over x and then up 5. Okay, so 0 reflected is still 0, and then up 5 would put it right there. Reflect it to negative 1, up 5. Reflect it to negative 16, up 5, we're now at negative 11. Okay, reflect it, move it up 5. Reflect to negative 16, move it up 5. So because it's still centered around the y-axis, because we didn't shift it left or right, this one happens to still be even. So sometimes when you do an HK shift, it still remains even or odd. Sometimes it changes. You really just have to make sure you're checking your graph or checking some ordered pairs to make sure. Okay, what if I told you you had the following graph and you had to come up with the equation for it? And I told you that it was quartic, meaning the fourth power. Okay, so we're going to have to do some variation of this. Well, we can see that it went right 1. We have to assume 1 because there's no labels, and up 1, 2, 3, 4, 5. So because of the right 1, we're going to have x minus 1. We have to keep the fourth power because that's what gives us the shape. And then we had that up 5. But there could have been an a value. So that's where a second ordered pair comes in. I'm going to use that one, 0, 4. So 4 for the y. And I find that when students have a problem where they have a variable and a multiplier, if they leave it in this order, they're going to make a mistake. So I'm going to really quick switch that up by flip-flopping the multiplying order. That's that commutative property. And I wrote 4 when I should have wrote 1. 0 minus 1 is negative 1, to the fourth power is positive 1. So 4 equals 1a plus 5. Subtract 5. I don't have to write the coefficient of 1. Now we know our a value is negative 1. So the equation of this line is f of x, sorry, not a line, but the polygon, or the, not the polygon, the polynomial is negative 1, x minus 1 to the fourth power plus 5, or negative x minus 1 to the fourth power plus 5. Either way of writing it is very suitable.
Thanks for learning with me here on Math with Michelle. If this helped, give it a like and don't forget to subscribe for more clear and simple math lessons. Got a question or topic you want me to cover? Drop it in the comments. Until next time, keep practicing, stay curious, and remember, you've got this.